Hi everyone, welcome back to the Block 11 video series. You may be familiar with the fish harvesting problems from the second written assignment. In this video, we continue this topic and see how optimization problem can be applied for sustainable harvesting. By the end of watching this video, you will be able to find optimal harvesting rate, and also you will be able to judge the interrelations of key quantities. For many natural fish populations, the net number of new recruits to the population in a year can be modeled like this function. R of n is equal to R times n times 1 minus n over k. By the way, the main reference for this topic is written by Clark, The Economics of Overexploitation. So here n, the capital N, the independent variable, that is the input variable, represents the existing population size. R and K are parameters, that is these are constants determined by the specific case. R of n is the net number of new recruits depending on n. We know that if R of n, that's the number of recruits, is positive, we have some recruits and so the population will increase. On the other hand, if R of n is negative, the population will decrease. We can see this mathematically as follows. So if n is between 0 and k, R of n is positive, therefore population increases. If n is greater than the parameter k, R of n is negative, so the population decreases. When k is equal to n, R of n is 0, so the population stabilizes, so there is no change in population. So the constant k is known as the carrying capacity. Now suppose the population is subject to harvesting with the following model. So the capital H is equal to small h times n, where the small h is a measure of the fishing effort and the big H is the total harvest rate. We want to answer to the following very important questions. First, determine the fishing effort to have the largest possible harvest rate once the population has stabilized. That is to say, we want to optimize this harvesting with the population has stabilized. So we want to have sustainable harvesting. The second question, what are the population size and the total harvest if this optimal fishing effort is used? So I introduced this diagram in my lectures to help you to practice solving a problem systematically. So there are 4 steps. First, clarify the question. So let me say it is the Q step. And second, do math modeling, M step. And solve math problems, S step. Finally, analyze the math solution, A step. Okay, so let's take the steps. The first step, Q, clarify the question. So the question is, determine the fishing effort to have the largest possible harvest rate once the population has stabilized. The second step, M, make a model, math model. There are 3 sub-steps that you may want to take in these steps. So draw diagrams if possible, introduce notations, and distinguish known from want. And for our case, it's a bit difficult to draw diagrams, and also the notations are all introduced. So let's distinguish known from want. So there are 2 known facts. First, the population has stabilized, which means mathematically R of n is equal to H. The number of recruits should be equal to the harvesting, the total harvesting. Please note that without harvesting, to have the population stabilized, R of n should be 0. However, with the harvesting effect, to have the population stabilized, R of n should be equal to H. Now, we want to have the largest possible harvest rate. And we learned this means mathematically the derivative of H should be equal to 0. And what we want is to find the value of the fishing effort in this case. Okay, so now third step, we just solve this math problem. Okay, so from this first fact, R of n is equal to H, we have the following equation by replacing R of n and H by their formula. So from this equation, we can solve for n as a function of small h, the fishing effort. Now let's move on to the second fact. The derivative of the total harvesting rate should be 0 when we differentiate it with respect to h. So please remember the formula of the capital H is small h times n. So by replacing n by this new function in h, we can differentiate the capital H with respect to small h. By solving this equation, we can get the value for the fishing effort, which is equal to R over 2. So we found R of 2 is a critical number for this function h, and now we notice that the derivative of h is positive when small h is less than R of 2, and the derivative of h is negative when the small h is strictly greater than R of 2. So by the forced derivative test, we know the capital H is actually maximal when the small h is R over 2. So we can guarantee that the value R of 2 is what we want. So we finished solving this math problem. Now, do not forget the last step. We need to analyze this math solution. So how can we analyze this? Simply, we just state what we found. Once the population has stabilized, we can have the largest harvest rate when the fishing effort is equal to R over 2. Okay, so let me leave the second problem for you. Thank you.